Hi everyone! We are now down to our 18th lesson, which is the moment of inertia of composite figures for this course, statics of rigid bodies. So for this lesson, students must be able to solve the moment of inertia of composite figures. Okay, so let's start our discussion. Okay, so again, these are the moment of inertia of common geometric figures for rectangle, for triangle, for circle, semicircle, and quarter circle. So memorize all these because we are going to use them, okay, in our computations for this topic. Okay, so for moment of inertia for composite areas, when a composite area can be divided into geometric elements such as rectangles, triangles, circles, semicircle, quarter circle, etc., for which the moments of inertia are known, the moment of inertia for the composite area is the sum of the moments of inertia of the elements. However, they must all be found with respect to the same axis. So we are going to use the concept of transfer formula here. Okay, so let's say we have a composite area. So that composite area, let's say it is composed of different geometric elements such as rectangle, triangles, etc. Okay, so if we are going to solve for the moment of inertia of that composite area with respect to x or y axis, okay, so we are going to use the concept of transfer formula. So for each geometric element, no, for each geometric element, we are going to solve, no, for its moment of inertia with respect to the x-axis. Okay, so we are going to use the transfer formula for that. No, so we know the established centroidal moment of inertia, no, for geometric elements such as rectangle, triangle, circle, quarter circle, no. So we are going to use that, and we are going to add AD squared. No, we are going to add AD squared, no, and we are going to solve, no, this, no, the this formula, no, for each shape or for each geometric element in that composite area, okay, and sum them up. Okay, we are going to sum them up. Okay, so Ix will be equal to the summation of Ix bar plus AD squared, and then Iy, that will be summation of Iy bar plus AD squared, no? Okay. Okay, so let's solve sample problem. Determine the moments of inertia with respect to the centroidal x and y axis of the wide flange beam section shown below. Okay, so this is the wide flange beam, no? So this is the section of the wide flange beam. Okay, so this is actually in I shape, no? This is in I shape. Okay, so we are going to solve for the moment of inertia, okay, of this wide flange beam with respect to the x centroidal, x and y centroidal axis. No, so this is the x centroidal axis, okay, and this is the y centroidal axis. So as we can see here, this wide flange beam, this is actually symmetric, no, upward and downward, and also at the left and at the right, no. So we can just say that its centroid is located at the center, no, of this beam, no, of this wide flange beam section. Okay, so this will be the location of the centroidal x-axis and the centroidal y-axis. So we are going to solve the moment of inertia, no. So the moment of inertia with respect to the x-centroidal axis. So we are going to analyze, no, this figure. So this is actually a composite area. This is a composite figure, no. So we can divide, no, this composite area, no, into three rectangles, no. This way, this is the first rectangle, this will be the second rectangle, and this will be the third rectangle. So to solve for the moment of inertia of this composite area, we have to solve for the moment of inertia with respect to the x-centroidal axis of each area, of each rectangle. Okay, so for this rectangle, so actually this is just the same, no, with this rectangle. Okay, we can just actually solve for one of these rectangles and just multiply it by 2, no. So let's say if we consider this rectangle, now, if we solve for the moment of inertia of this rectangle with respect to this x-axis, which is the excentroidal axis, no? We need to use transfer formula for that, right? So the transfer formula for that, we know the excentroidal moment of inertia of this rectangle, and then add AD squared, no? The transfer term. Okay, so that we can transfer that excentroidal moment of inertia to this x-axis, no, which is the excentroidal axis of this entire section. Okay, so that's how we do it. But here in this case, for this rectangle, no, as we can see here, no need to transfer the excentroidal moment of inertia of this rectangle because the reference axis here, okay, is already at the centroid of this rectangle. So this will just basically be the excentroidal moment of inertia of this rectangle, which is bh cubed over 12. Okay, so that's how we do it. So let's solve this. Again, we are going to solve for the moments of inertia with respect to the x-centroidal and y-centroidal axis, no? So this is the x and y-centroidal axis, no, of this composite, composite area. Okay, so for our solution, for the first one that we're going to solve, that is the moment of inertia with respect to the x-centroidal x-axis. So we can actually have two solutions here. Okay, so for the first solution, so again, we are going to use this, no, that the moment of inertia of this composite area with respect to the x-centroidal axis, that will be equal to the summation, okay, of the x-centroidal moment of inertia, okay, of each area here, no, of each area that compose the composite area plus its transfer term, no? So we will transfer them if needed. Okay, so if the centroid of that area is not located at the centroidal axis that we are that we are considering as the reference axis. Okay, so this will be the formula. So we will first solve this, no, the centroidal moment of inertia of this rectangle. So this rectangle, no, so this is actually the web, no, of this wide flange beam. So this is the web. So this is a rectangle wherein its dimension, its thickness is 1. So this will be the base, which is 1, and its height is 10. Now, so its base is 1 and its height is 10. So its x centroidal moment of inertia, okay, with respect to the to the axis of this rectangle alone. Okay, so that is bh cubed over 12, right? That is bh cubed over 12, and we don't need to have a transfer term here because as you can see here, if you use transfer term, the distance d will just be 0 because the distance d, that will just be the distance of the centroid of that area, no, and the reference axis. Okay, so in this case, the centroid of this rectangle is actually at the reference axis also, so that will just be 0. So I just showed you here that this, no, so that you can understand and figure this out. So this will just be 0. So its an x-centroidal moment of inertia will be bh cubed over 12, no, for this rectangle. Now, for the two rectangles here, this one and this one, so we will just consider one. So this will just be equal since they are symmetric. So their distance then, no, their distance d will also be the same naman, no. So we will just multiply them by 2, no. We will just consider one of this rectangle. So in this case, let's consider this rectangle. So this rectangle, no, its base is 8. No, its base is 8 and its height is 1. Okay, so we are going to use the excentroidal moment of inertia, no, for this rectangle. So its excentroidal moment of inertia is bh cubed over 12, no, bh cubed over 12, but we need to transfer that excentroidal moment of inertia to this axis. Now, since this will be our reference axis here, this x-axis, so there will be a transfer term here. That's why we're going to add AD squared here. So our area here, so the area of this rectangle is base times height, so that will be 8 times 1. And its distance d, no, will be the distance of the centroid, no, or the distance between the centroid of the rectangle and the reference axis. Okay, so the distance d will be this distance, Okay, so the centroid will be located here. The centroid of the rectangle will be located here. So this is 0.5, right? This is half of 1. So this is 0.5 plus this distance. So this distance is half of 10. This is half of 10. So this will be 5. So 5 plus 0.5, that will be 5.5. So this is actually located above the x-axis. No? So this will be positive here. But actually, we can just we can just disregard the sign, because even if it's located below, no, so even if it's negative, since we will square it, no, it will just be canceled, that negative, no, so we can just disregard that sign, no, that sign convention for this, no. But anyway, so to solve this, no, uh inputting this in our calculator, so this will give us 568.67. So take note that the unit for moment of inertia is to the fourth, unit to the fourth. No, since we have here area times distance. Area times distance is area is unit squared, tapos distance squared, so that will be unit to the fourth na, diba? Also for this. So this is BH cube, right? B, so base, and H cube. So that will become unit to the fourth, ha. So again, the unit for moment of inertia is unit to the fourth, ha. So in this case, this is inches. No, so this will be inches to the fourth. So this will now be the answer for the moment of inertia with respect to the centroidal axis, no. So we can actually have solution 2 for this, no. So if we are going to analyze this, no, we can solve this by even without using transfer formula or transfer term. Okay, so as you can see here, this will this can be a rectangle. Okay, this this with base B, and its height will be 10 plus 1 plus 1, so that will be 12. So we can just actually subtract. No, we can just solve for the moment of inertia of this rectangle, since this is its centroid is located at the reference axis where we solve the moment of inertia. So the distance d will just be 0. So we will just need the centroidal moment of inertia of this rectangle alone. Okay, and if we just subtract these two rectangles, as you can see, these two rectangles, right? These two rectangles. So its dimension, this rectangle, its dimension is 10, and then this base is actually 8 minus 1, no, 8 minus 1, then divided by 2, so that will be 3.5, no? So that will be, tama ba? 8 minus 1, that will be 7 divided by 2, so that will be 3.5. No? So that will be the dimension of this rectangle. So if we solve for the moment of inertia of these two rectangles, okay, with respect to the x-axis, so the distance d will also be 0. Right? It will be 0 because the centroid of this rectangle is at the centroidal axis or the reference axis. So the distance d will be 0. And if we just multiply it by 2 and then subtract these two rectangles nga, no, from the this big rectangle, so it will produce this this wide flange beam section. No, so we can do that because the distance d will just be 0. Okay, so the solution will be easier. It will be shorter, no? But in this case, I just included lang din, no, this um transfer term, no, just for you to see it. But we can just actually disregard this distance, this transfer term, because the distance nga dito are just 0, no. So we will just use the centroidal moment of inertia alone of the rectangles involved here. So this will be the centroidal moment of inertia of the big rectangle, which is BH cube over 12. So the base is 8 and the height is 12. So that will be 8 times 12 cube over 12. And then for this one, okay, so for this one, we will subtract. No, we will subtract the moment of inertia of these two rectangles, since this is not part of the shaded region. So the moment of inertia that we are just solving is the moment of inertia of the shaded region. No? So we will subtract this. So this will be minus. We multiply it by 2 since they are just identical. So we will just consider one one rectangle. No, so its base again is 3.5 and its height is 10. So BH cube over 12. Okay, so that will just be 3.5 times 10 cube over 12. Okay, so solving for this will just be the same. Of course, it should be the same as well. Okay, so this is also 568.67 inches to the fourth. So it depends on you, okay, which solution you're going to use, no? So actually, if you already mastered this topic, uh, of course, will be the advisable that you use because it is shorter. But if you are just a beginner, no, if you are just new, no, to solving such problems, no, you can just stick to solution 1. No, so you will never go wrong naman, no, by using solution 1. Okay, so it depends on you, okay? Okay, so for letter B, so we are going to solve for the moment of inertia with respect to the y centroidal, okay? Y centroidal moment of inertia with respect to the y centroidal axis. So this is the y centroidal axis. So we are going to solve for its moment of inertia. Okay, so for our solution for this, no, so this will be our formula. So the moment of inertia, okay, with respect to the y centroidal axis, that will be equal to the summation of the moment of to the summation of the y centroidal moment of inertia of each area, okay, plus the transfer term, no, if applicable. Okay, so let's start solving this, no. So in this case, this will be our this will be our reference axis. Okay, this will be the y centroidal axis, no. So as you can see here, all of these rectangles, okay, the centroid of all this rectangle, no, they pass through or this y-axis, no, this y-axis, this passes through the centroid of all these rectangles. So meaning to say, no need to add transfer term because it's already at the centroid. No, so in this case, we are just going to solve for the centroidal moment of inertia of each rectangle. No, so for this rectangle, so again, the dimension for this is 10 and then 1. No, so its base is 1, its height is 10. So hb cube over 12. So this will be hb cube over 12 since our reference axis is y, ha. Okay, so this will be hb cube over 12. Okay, so no need to add this because the distance d will just be 0 nga, no? So I just included this here, no? But you can just disregard that. Okay, and also for the two rectangles, this rectangle wherein its base is 8 and its height is 1. So same here, no? So we will just multiply them by 2, no? Since they are identical. So this will just be hb cube over 12 as well, no? And this will just be 0. So solving for this, so the y the moment of inertia of this composite area with respect to the y centroidal axis is 86.17 inches to the fourth. Okay, so if you are going to analyze this, ha, okay, so if you are going to consider this, no, so let's say this is the x-axis nga, the x centroidal moment or x centroidal axis. So if you're going to solve for its moment of inertia with respect to this axis, the moment arm, no, will actually be longer, no, than the moment arm if we solve for the moment of inertia wherein the reference axis is y, right? So this will have a longer moment of inertia. That's why its moment of inertia is greater, no, than the moment of inertia of the with respect to the y centroidal axis because the moment arm is larger. But it's case to case, no. So you can check your answer, no, based on the figure and the moment arm. No, so that you can just check if your answer is logical. So in this case, we can say that our answer here naman is logical. Okay, so let's compute the moment of inertia for the composite area shown with respect to the indicated x-axis. So the indicated x-axis is here. Okay, so this is 2 centimeter from here, no? Okay, so this will be the reference axis, no, wherein we are going to solve the moment of inertia. So to solve this, no, we have to divide, no, this composite area, okay, into geometric elements. No? So the geometric elements here, no? So this is a rectangle, no, wherein its base is actually this side, no, so this side is actually the diameter of this semicircle, no, so this will be 6 centimeter, okay, and we have here a geometric shape or figure semicircle, no, and we also have here a triangle. Okay, so we are going to solve for the moment of inertia of each geometric figure, no, of each geometric shape with respect to this x-axis. So we are going to apply transfer term here or transfer formula here. Since these shapes, no, these areas, no, their centroids, there will be a distance d, no, from that centroid to this x-axis, which will be the reference axis, okay, of the moment of inertia that we are going to solve. Okay, so let's start solving this. Okay, so to solve this, so we can divide, no, this composite area into semicircle, into rectangle, and into triangle. So the triangle here, the dimension will be, the height is 9 centimeter, and the base will be 9 minus 6. So this will be 3 centimeter. Okay, so we can actually construct a table here. Okay, so we can construct a table here, no, and solve for its Ix bar, no, since we are going to to solve for the moment of inertia with respect to the x-axis. So the formula here will be Ix bar is equal to the Ix bar of each shape, no, plus the transfer term, which is AD squared. No, so in this case, for the Ix bar of this semicircle, no, so this is a semicircle. So it's Ix bar, no, so from the table, so you have to check from the table, no, the orientation also. So our Ix bar from the table, no, considering the orientation, will be the 0.11 r to the fourth, no. So in this case, the radius here is 3 centimeters, so this will be 0.11 3 to the fourth, and that will be 8.91. Okay, so for rectangle, no, its centroidal moment of inertia, centroidal moment of inertia is bh cubed over 12. So in this case, the base is 6 and the height is 9. So this will be 6 times 9 cubed over 12. So this is 364.5. Now for the triangle, no, for triangle, the centroidal moment of inertia is bh cubed over 36. No, so this will be 39 cubed over 36. So that is 60.75. Now for the area of a semicircle, no, so that is just 1/2 pi r squared. So that will be 14.13717. For rectangle, base times height, that will just be 6 times 9. So that will be 54. For a triangle, that will be 1/2 base times height. So the base is 3 and the height is 9. So 1/3 times 3, 1/2 rather, times 3 times 9. So that will be 13.5. Now for the distance d, so the distance d, this is the distance of the centroid of each shape, no, and the x-axis. No, so that will be the the reference axis, which is the x-axis. So for this semicircle, so this is the semicircle is located here. Okay, so the centroid of this semicircle is located somewhere here at this point. No, so we will measure this, the distance of this point up to the reference axis. No, so this distance, we need to know this distance. So this will just be this distance. No, so from the centroid. No, so this is the y coordinate of the centroid. So this is 4r over 3 pi, right? No, so this is 4r over 3 pi plus 2. No, so that will be 2 plus 4r over 3 pi, wherein the radius is 3. Okay, so this will be 3.27324. So that will be the distance d of the centroid of the semicircle to the reference axis. Okay, so that is the distance d. Now for the rectangle, so this is the rectangle. Okay, and this is the x-axis. So the rectangle is 9 centimeter. Okay, so if this is 9 centimeter, okay, this is 9 centimeters. So the centroid of the rectangle, okay, will be somewhere at this point. Okay, so this is actually 4.5, right? This is 4.5. So the distance that we need is from this point up to the centroid. So to solve that, no, so that will just be 4.5 minus 2. No, so this will be that value, 4.5 minus 2, so that will be 2.5. But since that point is actually located below the reference axis, so that will be negative. So this will be negative 2.5. But in this case we can just disregard this, no, because distance t will just be squared. So negative 2.5, if you square that, that will just be positive then. Okay? So also for the triangle, okay, so the distance d of the triangle, so its centroid will be located somewhere here. Okay, so we know that this point, no, this distance from the tip, that will be two-third of 9, right, of this side of the triangle. So this is two-third of 9. This point, no, the distance from this tip of the triangle up to the point of the centroid. So that is two-third of 9. No, so the distance that we need is from the x-axis to the centroid. So we will subtract 2, no, from two-third of 9. So that will be two-third of 9 minus 2. So that will be 4. So since the centroid is located below the x-axis, the reference axis, so that will be negative. But we can just disregard that because we will just we will square that, no? So that will just become positive din naman. So applying our formula, no, to solve for the moment of inertia with respect to the given x-axis, no, so we will just sum up all ix bar and d squared, ad squared, no, plus ad squared. So for the first one, no, so its ix bar is 8.91 plus its area is 14.13717 times d squared. Our d squared is 10.71410. So it will be, we will sum up, no, this one then. So this is 364.5. This is the ix bar plus its area is 54 times its d squared, which is 6.25, plus the third one, this is 60.75 plus 13.5 times d squared, which is 16. So solving for this, so the moment of inertia with respect to the given x-axis is actually 1,139.1, and don't forget to include the unit. The unit for this is centimeter to the fourth. Okay, so this will now be the answer for this problem. Let's proceed now to the third sample problem. A rectangle is 3 inches by 6 inches. Determine the polar moment of inertia and the radius of gyration with respect to a polar axis through one corner. So there is no given figure here, no, but from the description, no, given in the problem, so we have here a rectangle, and the rectangle is 3 inches by 6 inches. So this is base times height, no, base by height. So 3 inches will be the base and 6 inches will be the height. Okay, so we are going to determine the polar moment of inertia. So the polar moment of inertia, that is the moment of inertia with respect to the axis that is perpendicular, no, to the plane. No, so that will be the z-axis. No, so we are going to measure that. So we already discussed that from our previous recorded video discussion. No, so you can check that out. No, if you don't follow me here. No, if you cannot follow me here. No, so okay, so you have to watch that first. No, okay, so and the radius of gyration. So we will determine the polar moment of inertia and the radius of gyration with respect to the polar axis. So our perpendicular axis here, no, perpendicular to the plane, will be at one of the corners of this rectangle. No, so that we will analyze that. No, so let's solve this problem. Okay, so for this problem, no, to solve this, no, so we will first draw, no, the rectangle described in the problem. So the base is 3 and the height is 6 inches, no. So we are going to solve for the polar moment of inertia. So this is the moment of inertia with respect to a polar axis through the one corner. So we can consider any of these corners, no? Any of the corners of this rectangle. So in this case, let's consider this corner. So it will just give you the same answer naman, no? So if you consider this corner, so the axis, no, the perpendicular axis that we are going to use as the reference axis will be the axis perpendicular to this point, no, perpendicular to this plane. No, so what the x and y axis that we need here is this x axis and this y-axis, no, since the reference perpendicular z-axis here is here, No, so our x-axis is here and our y-axis is here. So if you will recall, no, for the formula of polar moment of inertia, that is actually Jz is equal to Ix plus Iy. No, so we just need to solve for Ix and Iy. So in this case, for the moment of inertia with respect to the x-axis and y-axis of this rectangle, no, this is already established actually. No, if the given x-axis is at the base, no, of the rectangle, no, so that is directly bh cube over 3. No, but also you can ano naman, you can use transfer formula here. No, you know the centroidal moment of inertia of this rectangle, and you just transfer that to the x-axis, to the given x-axis, no. So it will just be the same. That will just be the same with bh cube over 3 naman, no. Okay, so directly applying this, no, to solve for the moment of inertia of this rectangle with respect to the x-axis. So this will just be 3 times 6 cube over 3. So this will now be the Ix. Now for the Iy, no, so this will now be with respect to the y-axis. So this is already established, no, from the table. No, so this will just be hb cube over 3. So hb cube over 3 is 6 cube over 3. So that will be 54. So solving for Jz, that will just be Ix plus Iy. So that will just be 216 plus 54. So that will be 270. So don't forget to include the unit. That will be inches to the fourth. So this will now be the answer for this problem. Okay, also for letter B, no, we have to solve for the radius of gyration. So from our previous discussion, recorded video discussion, the formula for radius of gyration is k is equal to square root of I over A. So the I here is the moment of inertia. So we will use the polar moment of inertia that we solved from here. So this will be 270. And the area of this one is base times height. So that will be 6 times 3. Okay, so solving for this, this will be 3.87298. So the unit for this is inches, ha? Since the unit for moment of inertia is inches to the fourth, and the unit for area is inches square, no? So it will just become inches squared, okay? And if you square root inches squared, so that will just be inch, no? Okay, so this will now be the answer for the radius of gyration with respect to a polar axis through one corner. Okay. Okay, so let's proceed now to sample problem number 4. A hollow square cross-section consists of an 8 inches by 8 inches square from which is subtracted a concentrically placed square 4 inches by 4 inches. Find the polar moment of inertia and the polar radius of gyration with respect to a z-axis passing through one of the outside corners. Okay, so we have here a hollow square cross-section. Okay, so this is the 8 by 8 inches square. Okay, so as mentioned in the problem, there is a subtracted concentrically square 4 by 4 here. No? So this is subtracted from the center, okay, of this 8 by 8 square. No? So this will be subtracted. No? So the area that we're going to consider here is just the shaded region. Okay, so what we're going to solve here is the polar moment of inertia, okay, and the polar radius of gyration, okay, with respect to the z-axis passing through one of the outside corners. So in this case, we can consider any corner here. So in this case, we will consider this corner. So this is where the z-axis passes through, no? The z-axis is perpendicular to the plane. Okay, so this is perpendicular to the screen, no? As you look at it now, no? So the x-axis will be located here if the z-axis is here and the y-axis is here. So let's solve this. Okay, so for this problem, okay, so this is the first one that we're going to solve is the polar moment of inertia. So we are going to solve for Ix and Iy since the formula for this is Jz is equal to Ix plus Iy. Now for Ix, no, so actually since this is a square, no, this is a square and the hole here or the punch here is also a square, no, so meaning to say the moment of inertia with respect to x and y axis will just be equal. They will just be the same. No? So we can say that Ix equal to Iy. So for its moment of inertia, no, with respect to, let's say, to x-axis, okay, so what we're going to do here is solve for the moment of inertia, okay, of this square. No, so this is actually a rectangle generally, right? So since we know already the moment of inertia of this rectangle generally, no, since the x-axis is at its base, so that will just be bh cubed over 3. No, so no need to use transfer formula. Okay, because it's already established naman. But you can also use ano naman, you can also use transfer formula if you want, no? So this will just be 8 times 8 cubed over 3. Okay, and what we're going to do here is subtract the moment of inertia of this hole, no? With respect to the x-axis. So in this case, we have to use transfer formula here. Since there's a distance d of the centroid of this square, no, to the reference axis, which is x, no. Okay, so this will be the centroidal moment of inertia of this square is bh cubed over 12, okay, plus ad squared. So its area is 4 times 4, and its distance d. So this will be this distance from this point up to this point. So this is just actually ano naman, half of 8, no? So this will just be 4 then. So that will be 4 squared. So this is ad squared, ha? Okay, so solving for this, no? So the value for Ix and Iy, so it will just be the same because ano nga, this is a square naman, no? So if you try to solve for Iy, so for bh cubed, so it will just be hb cubed rather, so it will just be 4 times 4 cubed din naman, no? So they will just be equal. So they will be both 1,088 inches to the fourth. So solving now for JZ, so that will just be 1,088 plus 1,088. So that will be 2,176. So the unit for this is inches to the fourth. So this will now be the answer for this. Now, for the polar radius of gyration, we will just apply our formula. Okay, so this will be square root of I over A. Our I here is the moment of inertia, so that will be 2,176 over the area. So in this case, the area that we're going to consider here is just the shaded region. So this will be 8 times 8 minus 4 times 4. So solving for this is 6.73300 inches. So you can now box that, no? So this will now be the answers. Let's proceed now to sample problem number 5. Find the centroidal moment of inertia along the x-axis of the trapezoid shown below. Okay, so this is the given trapezoid. Okay, so we are going to solve for its moment of inertia with respect to the centroidal x-axis. So this is the x-centroidal axis. Okay, so in this case, no, so we don't know yet the location of this x-centroidal axis. No, so we have to solve that. No, we have to solve for this y bar. Okay, so let's solve this. So again, to solve this, no, to solve for the centroidal moment of inertia along the x-axis, we need to locate first or determine the location of the x-centroidal axis. So in this case, to determine this location, no, we need to solve for this y bar. So to solve for this y bar, no, we will need to solve for the centroid, no, of this composite area of this trapezoid, no, and our reference axis to solve for y bar will be the base of the trapezoid, no. So this will be the reference axis to solve for y bar. So applying the solution, no, in solving for centroid, no, of composite area, so that will just be ay bar is equal to summation of ay. So area here will be the total area of this composite area, and then we will equate times y bar, so we will equate that to the summation of all the area of each shape here times the y coordinate, no, the y coordinate of each shape with respect to the base, no, which will we use, no, as the reference axis. Okay, so the total area of this trapezoid will just be the area of this is rectangle. So this is actually square since the dimension here is both 6, no? Okay, so this is a square. Okay, and also we have here two triangles, no? So we are going to solve for their area. So the area of the square is 6 times 6, and then the area of the triangles, so they are identical naman, so we will just multiply it by 2. So the area of one triangle here is 1/2 base times height. So the base is 6, and this the base height, that is height actually 6, and then its base will be, since this is 18 centimeter and this is 6 centimeter, so this is equal and this side is equal, so this will just be 6 centimeter, no? Okay, so that will be 1/2 base times height, and then we just multiply it by 2 since we have two triangles here. Now times y bar is equal to, so we solve first for the AY, no, of the square. So for this square, its area is 6 times 6, and its y coordinate, no, from the reference axis, which is from the base, no, so that will just be half of 6, so that is 3, no, plus the AY of the two triangles, so we can just multiply it by 2, no, and consider just one triangle, no. So if we consider this triangle, so its area is 1/2 times 6 times 6, and its y coordinate from the base, okay, so that is actually 1/3 of 6, no? That is 1/3 of 6. So the 1/3 of 6 is 2, no? So this will be 2. Okay, so solving for y bar, no? So this will be 2.5 centimeters. So the location of our x-centroidal axis here, okay, is 2.5 centimeter from the base. Okay. So we can now solve for the moment of inertia with respect to the x-centroidal axis. So to solve that, no, since this area is composed of a triangle, a square, and a triangle also, okay, so we will use a summation of the centroidal moment of inertia of each shape plus their transfer term, no, if needed. Okay, so in this case, okay, for this square, no? So the centroidal moment of inertia of this square is BH cube over 12, no? So BH cube over 12. So the centroid of this square is actually 3 centimeter from here, right? 3 centimeter. So since this is 2.5, no? This from the base to this axis. So meaning to say, there is a distance between the centroid of the square, no, and the reference axis, which is this axis, no? So there will be a distance. So that distance is actually 3 minus 2.5. So that will be 0.5. So that will be 0.5 distance squared. So that will be 0.5 squared. Okay, so this will now be for the square. Now for the triangle, okay, we can just analyze one triangle here and just multiply them by 2, no? Since these two triangles are just ano naman, identical. Okay, so for this triangle, no, its centroidal moment of inertia is BH cube over 36, no? And the centroid of this triangle is actually 1/3 of 6, no? So that is 2. 2 from the base, so 2 centimeter. So meaning to say, there is a distance, no, from the excentroidal axis, from this excentroidal axis to the centroid of the triangle. So that is 2.5 minus 2, no? So that is 0.5. Since it is located below the reference axis, so it will be negative here. But since it will just be squared naman, so it will just be positive pa rin. Okay? So, solving for this, no? Okay, so the moment of inertia with respect to the excentroidal axis, no, given in this problem is 198 centimeter to the fourth. So this will now be the answer. Okay, so for sample problem number 6, okay, determine the distance D at which the two 3 inches by 8 inches rectangles shown should be spaced so that IX bar is equal to IY bar. So this is the distance D that is being mentioned in the problem. So we have to determine this distance D in such a way that IX bar and the IY bar of these two rectangles, okay, will be equal. No? So we will use this equation, no, for our solution, that the IX bar, okay, of these two rectangles, okay, is also equal to the IY bar of these two rectangles, no? So, upon using this equation, no, we can solve for distance D because distance D will be incorporated, no, in this solution, in this equation. Okay, so let's solve this problem. Okay, so again, we are going to find distance D. Okay, so we are going to use the given equation here that the Ix bar and the Iy bar, no, of these two rectangles, okay, they are equal, no. So Ix bar, that is the moment of inertia with respect to the x centroidal axis, and Iy bar is the moment of inertia with respect to the y centroidal axis. So the x and y centroidal axis here are this axis, no, axis. So this is the x centroidal axis, and this is the y centroidal axis, no. So this is just at the the centroid, no, of these two rectangles, no. So this is at this point, no. Okay, so using this equation, no, let's solve for Ix bar. So to solve for Ix bar, okay, for these two rectangles, so our reference axis here will be this, will be this x-axis. Okay, so this will be the x-axis. Okay, so this will be the reference axis. Okay, so for this rectangle, actually they are they are identical. These two rectangles are identical. So we can just solve for one rectangle and then multiply them by 2. No, so multiply that by 2, no. So let's say we consider this rectangle. Okay, so its centroidal moment of inertia, okay, is BH cube over 12. Okay, and the centroid of this rectangle is not located at the reference axis. So we need to apply transfer formula here. So we need to add transfer form, no? Okay, or term, transfer term. Okay, so we're going to determine the distance D. No, distance D is the distance between the centroid and the reference axis. So the distance D here will be this distance. So this distance is half of the height of the rectangle. The height of the rectangle is 3. So this is 1.5, and then we add this distance. So this distance is actually half of D. So this is D over 2. No, so the distance D, no, the distance between the centroid and the reference axis is D over 2 plus 1.5. Okay, so we will apply transfer formula, ha. Okay, so that is BH cube over 12 plus our area is 8 times 3. And then our distance is D over 2 plus 1.5. So we will square that. Okay, so we will multiply it by 2 since there are two rectangles here. Okay, so we will equate that to Iy bar. So solving for Iy bar, so for the moment of inertia of these two rectangles with respect to the y centroidal axis, which is this axis. Okay, so as we can see here, the centroid of these two rectangles, okay, their centroid is already at the reference axis, no? So meaning to say, we don't need distance D here. Okay, so distance D will just be 0. So this will just be directly the centroidal moment of inertia of these two rectangles. So these are two identical rectangles, so we will just multiply it by 2. So this is actually HB cube over 12. HB cube over 12. So our base is 8, right? Our base is 8. Our height is 3. So HB cube over 12, no? So that will be the centroidal moment of inertia with respect to the y centroidal axis, no, of these two rectangles. So the only unknown here is the distance D. So distance D, if we expand this, no, since we have a square here, no, so we can expand this. So D here will be quadratic, right? So there will be two possible values of D here, no? So solving for D, no, so you can use your calculator to solve for distance D. So there will be two values. The first value is 1.2817, and the second value is negative 7.2817. Okay, so here, with these two given, with these two possible values of D, no, we will choose which answer is logical. So in this case, it's not logical that our distance is negative, so there is no negative distance. No, so we will use d equal to 1.2817 inch as the answer. No, so this will be the answer for this. Okay. Okay, so let's proceed to sample problem number 7. Determine the moment of inertia of the area shown in the figure with respect to its centroidal axis. No, so the area here, no, is this area. So this is in I shape, no. Okay, so we are going to solve for the moment of inertia with respect to its centroidal axis. So in this case, we can say that the y centroidal axis will just be located somewhere here because the area at the left is just ano naman equal to the area at the right, no? So we can say that it's just at the middle, no? Here at this here at this line, okay? So this is the y centroidal axis. For x centroidal axis, we cannot say that it's just at the center, right? Because if we put the x centroidal axis here at the center, it will not be balanced, no? That the area above will not be equal to the area below. So our x centroidal axis will be a little bit lower than the center, no? So it will be located somewhere here. Okay, so we have to solve this. We have to solve the location of our x centroidal axis. Now, so we have to solve for this y bar. So this y bar, to solve this, no, we will use the base as the reference axis here, no, and we will just use the formula that we are using to solve for centroid of composite areas or composite figures. Okay, so let's start solving this. Okay, so for this problem, we are going to solve the moment of inertia with respect to x and y centroidal axes. Okay, so we have to determine first the location of the x centroidal axis. So to do that, we have to solve for y bar. So y bar, this is measured, no, from the base. So we will use this base, no, this base as the reference axis to solve for y bar. Okay, so this will be ay bar is equal to summation of ay. So the total area for this composite figure, so it will be the area of this rectangle. So the dimension of this rectangle is 6 by 1. Okay, so for this rectangle, the dimension of this is 1 by 12. And then for this rectangle, the dimension of this is 12 by 1. So we will solve for the total area by solving each area, no? So this will just be 12 times 1 for this, no, for this area. Okay, or this area, pwede din. Okay, so also 1 times 12 for this area. Okay, and then plus 6 times 1 for this area. Okay, so this will be times y bar is equal to summation of ay. So for the first rectangle, let's say for this rectangle, okay, so for this rectangle, so the area of this is 12 times 1, and its y, or its y coordinate, no, from the reference axis, which is at the base. So that is the y coordinate, no? So this will be 0.5. This will just be half of 1, no? Its distance, no? Or the y coordinate, no, from the reference axis, which is from the base, no? So that will be 0.5 plus the area of the second rectangle, okay, 1 times 12, and its y, okay, its y, okay, is from the from the base. So from the base, the centroid of this rectangle is at the center of 12. So that will be 6. So 6 plus 1, since that will be the y coordinate from the reference axis nga. So 6 plus 1, that will be 7. Okay, now for the third rectangle, this will be the third rectangle. Okay, so the area of this is 6 times 1. Okay, and its y coordinate, no, the y coordinate of its centroid from the reference axis, which is from the base. So this will be 0.5, no, half of 1, 0.5 plus 12 plus 1. Okay, that will be 13.5. Okay, so 13.5. So we can solve now here the value of y bar. So the value of y bar here is 5.7 inches. Now, so this will now be the location of our x coordinate. This is 5.7 inches from the base. So we will use that to solve for the moment of inertia with respect to the centroidal axis. So to solve that, we will use this formula. So the moment of inertia with respect to the centroidal axis, okay, will be equal to the summation of the centroidal axis of all the of each shape here, plus the transfer term, no, which is AD squared, no, if applicable. Okay, so we will start with the rectangle here, no. Okay, where did we start here? Okay. Okay, so okay, we will start here at this rectangle. Tama, no? So this is the first rectangle. So this is BH cube over 12, no? Since the centroid of this rectangle is not located at the reference axis, no? So we will transfer. So AD squared, so the area is 12 times 1, and the distance, okay, distance D will be, we know that this is Y bar, diba? This is 5.7. Okay, so if this is 5.7, okay, and the centroid of this rectangle is located here, so this is 1.5 from the bottom. 0.5 rather, the half of 1. So 0.5. So what we're going to do here is 5.7 minus 0.5 to determine this distance D. Right? So that will be 5.2. Okay, so that will be the distance of the centroid of this rectangle to the reference axis. Okay, so for the next rectangle, so this will be the next rectangle. So this is BH cube over 12. So the base here is 1 and the height is 12. Okay, and then the centroid of this rectangle is actually not located at the reference axis. No, so there will be distance D. No, so the distance D will be the distance of the centroid, okay, to the reference axis. So since this is 12, no, so this is 6 from here, no, 6 from here. So this is 6. Okay, so 6 plus 1, so that will be 7, no, from the bottom. And then if we subtract y bar, so we can solve for this distance, right? So that will just be 6 plus 1, so 7 minus y bar, which is 5.7. So that will be 1.3. So that will be the distance D. Okay, so AD squared, 1 times 12 times 1.3 squared. Now, for the last rectangle, so this is the last rectangle. So, the centroidal moment of inertia of this rectangle is BH cube over 12, wherein the base is 6 and the height is 1. Okay, BH cube over 12. And the centroid of this rectangle is not located at the reference axis, no? So there will be a transfer here. Okay, so the distance D will be from the centroid. So this will be 0.5 plus half of 12, which is 6. No, 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 no. So the distance D will be analyzed. Let's analyze this. So 0.5 plus 12 plus 1 minus y bar. Okay, we can solve for this distance. Right? So again, that is 0.5, 0.5 plus 12, 12.5 plus 1, 13.5 minus y bar. So the distance that will be solved from that is this distance. So that will be 7.8. So ano ko nga, input ko in the calculator. So again, that is 0.5 plus 12 plus 1 minus y bar, which is 5.7. So that is actually 7.8. No, so 7.8 will be the distance D. Now, solving this, no, we can solve for Ix bar. So Ix bar will be 855.3 inches to the fourth. So this will now be the answer for this. Now, for letter B, that is the moment of inertia with respect to the y-centroidal axis. So our y-centroidal axis is here. Okay, so this is more simple, no? We actually don't need a transfer formula here because as you can see, the centroid of each rectangle, okay, are located, no, is located, no, at the reference axis, which is the y-axis, this y-axis. So the distance D will just be 0. So for these rectangles, no, so for the first rectangle, this will just be HB cube over 12. Okay, hb cube over 12. So this will just be 0. So directly hb cube over 12. And then for this rectangle, hb cube over 12 as well. And for this rectangle, hb cube over 12. So this will just be 0. So I just included this here, no, so that you can see it here, no, that it will just be cancelled naman. Okay, so for IY bar, or moment of inertia with respect to the y centroidal axis, so this will be equal to 163 inches to the fourth. So as you can notice here, no, the Ix sub O that is greater, no, than Iy sub O, because here as you can see nga, if this is the x centroidal axis, okay, so the moment arm, if you're going to use the formula for moment of inertia, no, the moment arm will be larger, no, compared to the moment arm if the reference axis is y. Right? So basically, it will really produce a larger moment of inertia with respect to the x-centroidal axis. So we can say naman that our answer is logical. Okay. Let's proceed now to sample problem number 8. Two 12 inches, 20 by 7 pound channels are latticed together to form the section shown in the figure. So this is the figure. Okay, so these are the two 12-inch, 20.7 pound channels. No? So this is that channel and this channel. So they are latticed together to form this, this section. So determine how far apart the channel should be placed so as to make Ix bar is equal to Iy bar for the section. Refer to the table. So neglect the lattice bars which are indicated by the dashed lines. Okay, so as you can see here, no, there's a given table for the channel. Okay, so let's say for this channel, okay, so there is a given X bar. So this is the X bar, no? So this is measured from here. So this is the centroid. Here is the centroid of this channel. Okay, when the channel is oriented this way. No, so this is the centroid. So the X centroidal axis is this, and the Y centroidal axis is this. So the measure of this, no, okay, so this is X bar. So from this point, no, to the Y centroidal axis. So this is X bar. So it's in the table. Also, in the table we have here Ix bar and Iy bar. So these are moments of inertia, no, measured from the X and Y centroidal axis. No, so there's also given area, no, for this section, no, for so no need to solve for the area of this and also for the moments of inertia because they are already given here in the table, no. Same with the X bar, no, it's also given in the table. So we are going to use, no, this given values, no, here at the table to solve for this distance d. So we are going to use this equation, no, this given equation mentioned in the problem, that Ix bar is equal to Iy bar, no, equating this two, no, so distance d will be involved there, no, so we can solve for distance d, no. Okay, so let's solve this problem. Okay, so we are going to solve for the distance d. So this is the distance d. Okay, and we will use the equation given in the problem, that is Ix bar is equal to Iy bar. So these are the moment of inertias with respect to the X and Y centroidal axis, no, from the figure. No, so in this case, no, the centroid of these two channels will be located here. Okay, and the X centroidal axis will be here, and the Y centroidal axis will be here. Now we are going to solve for the moment of inertia with respect to the X centroidal axis, no, of these two channels. So in this case, we can just solve for one channel and then multiply it by 2, since these two channels are just identical, no, and placed symmetrically, no. So we will solve for the moment of inertia with respect to the X centroidal axis. So here, since the X centroidal moment of inertia of each channel, no, of one channel, okay, it's already given in the table. So as we can see here, No, so in the problem, that is a 12-inch, no, 12-inch, 20.7 pound channel, no. So we are going to use this for this, no, for this row, 12-inch, 20.7 pound channel. So these are the values, no, for area. So this is 6.03 inches squared. For IX bar, this is 128.1. For IY bar, this is 3.9. For X bar, this is 0.7. And Y bar, this is 0, no? So 0 yung Y bar. So meaning to say, our Y coordinate here is located at the reference axis um, directly, no? So there, that will be 0. Anyway, so solving for IX bar of these two channels, so considering only this one channel, okay, so its IX bar, it is 128.1, the centroidal moment of inertia, x-centroidal moment of inertia of this channel. But the centroid of this channel is located here, at this point, di ba? Okay, at this point. So we need to transfer. Now, we need to transfer this to no need to transfer pala. 0, no? Distance D. So, our reference axis here is X, centroidal axis. Okay, so the centroid is located at the reference axis. Okay, so what I'm saying is for, for Y axis, for Y centroidal axis. So, in this case, so for IX bar, so the distance D will just be 0. And then we have here the X centroidal moment of inertia of this channel, which is 128.1. Plus AD squared, so the distance D will just be 0 since the centroid of this channel is at the reference x-axis, no? So that will just be 0. And we will just multiply it by 2 since we have here two channels. Now for IY bar, so we will now solve for the moment of inertia of these two channels with respect to the Y centroidal axis. So this is the Y centroidal axis. Okay, so again, for the Y-centroidal moment of inertia of each channel from the table, that is 3.9. Okay, so the centroidal moment of inertia, so the centroid of this channel is here. So there will be a distance, no, from the reference axis. So we will need to transfer. So this distance, no, from the centroid of the channel to the reference axis, which is the Y-centroidal axis, will just be half of D over 2, and then this, no, this distance. So this distance from the figure, this is actually X bar, right? So this is X bar, so this is 0.70. So 0.70 plus D over 2. So that will be the distance that we need here. Okay, so the area of this channel, no, given here is 6.03. And then AD squared. So our D squared is 0.7T plus D over 2 squared, no, quantity squared. So the only unknown here will be distance D. So we can solve for distance D, no, by using your calculator. So our distance D, since it is square here, no, so if we expand this, this will become quadratic, no, our distance D, no. So there will be two possible answers for this. So the first one is negative 10.477 inch, and the second one is 7.6768 inches. So again, we are going to analyze if what is the logical answer here. So in this case, the logical answer here, okay, is the positive answer. So the distance D will be 7.6768 inches. So this will now be the answer for this. Okay. Okay, so for sample problem number 9, a plate and angle column is composed of 4 8 by 4 by 1 inch angles with the short legs connected to a web plate, 14 inch by 1 inch, plus 2 flange plates, each 18 inches by 2 and 1/4 inches as shown in the figure. Determine the values of IX bar and IY bar. Okay, so this is the given plate and angle column. No, so its composition are 4 8 by 4 by 1 angles. No, so these are the angles that are mentioned. These are 4 na 8 by 4 by 1 inch angles, no? Okay, and then also it has web plate. So the web plate is this plate. No, so this web plate, no, as mentioned in the problem, this is 14 inch by 1 inch. So this is 14, and then the thickness is 1 inch. okay, plus 2 flange plates. So the flange plates are these plates, no, these two plates, one at the bottom and one at the top. So this flange plate, this is 18 inch, so this is 18, and then the height is 2 and 1/4. Now same here. So what we're going to do here is solve for the Ix bar and Iy bar. So we have to locate first the X and Y centroidal axis. So in this case, as we can see here, our figure, this column is actually symmetric at the right and at the left, no, and also symmetric at the upper part and at the lower part. So we can say that the X and Y centroidal axis, no, are just at the center. No, its centroid is just at the center. So this is where the X and Y centroidal axes are located. Okay, so for this, now we are going to use the given table. No, so there is a table here for the 8 by 4 by 1 inch angle. No, so this is the table, the value for the values that for for the angle, no, for the area. Okay, so what we're going to do here. Okay, so the area of of each angle, okay, is 11, no? So this is inch, ha? This is 11 inches squared since the dimensions are inches here. Okay? And then our Ix bar, so this is the the orientation of this for these values, no, for this angle. So this is the orientation of the angle. So the centroid is located here. So the X centroidal axis is here and the Y centroidal axis is here. Okay? Now, for Ix bar, so this is the moment of inertia with respect to this X centroidal axis. So this is 11.6. For Iy bar, so this is measured from this Y centroidal axis, 69.6. And then our X bar, so this is our X bar, 3.05. And our Y bar, this will be the Y bar. So this is 1.05. So we are going to use this data, okay, to solve this problem. So again, we are going to solve for Ix bar and Iy bar of this entire figure, composite figure. Okay, so let's solve now Ix bar. Okay, so to solve Ix bar, we will need the data for the angle, no? Okay, but for this flange, no? So there is a dimension for this given, no? In the problem, no? Also for this web, no? This is also a plate. So the dimension for this is also given in the problem and also for this plate. Okay, so we are going to solve for the centroidal moment of inertia, okay, of each component, no, of this composite figure. So the components here are this rectangle, this angle, we will use this data, this rectangle also, this also a rectangle, and this rectangle. So for the first one, no, for Ix bar, for the centroidal moment of inertia of, let's say, we consider first this. Okay, so this is the first rectangle that we're going to to solve. So the centroidal moment of inertia of this rectangle, okay, is BH cubed over 12. Okay, and the centroid of this rectangle is actually located, okay, at the reference axis, which is this X centroidal axis, right? So meaning to say there will be no distance D. So the distance D will just be 0. So this will just be simply 1 times 14 cubed over 12. Now, for the next one, so the next one here, okay, are the angles, no? So, for the angles, no, so we have here 4 angles, but we can also just consider one angle and then multiply it by 4 since they are, they are identical angles and they are actually symmetrically placed naman, no, above and below and then at the right and at the left, no. So we can just, multiply it by 4. Okay, so for the centroidal, X-centroidal moment of inertia of one angle, okay, so let's say for this angle, no, so that it will be easier for us to see the orientation, no. So the X-centroidal moment of inertia of this angle from the table is 11.6. Okay, so we will use that. Now, the centroid, okay, the centroid of this angle is located here. right? So basically, it's somewhere here at this point, no? So there will be a distance d here. Okay, so the distance d here will be this distance, right? From the reference axis x sub o, right? So to solve this, so this will be the half of 14.5. So this is the half of 14.5. And then subtract y bar. So this is y bar, right? To solve for this distance. So again, that is half of 14.5. Okay, so 14.5 divided by 2 minus y bar. So our y bar here is 1.05 from the table. So the answer for this, that will be the distance d, no? And that is 6.2. Okay, so that will be AD squared, no? So our area for each angle is 11. AD squared, so that will be 11 times distance d, which is 6.2 squared. So we will multiply it by 4 ha, since we have four angles here. Okay, now for the remaining shape here, which is this rectangle, which are these rectangles. So the centroidal, eccentroidal moment of inertia of this rectangle, no? So we can just consider one rectangle since they are identical and they are placed symmetrically naman, no? At the upper part and the lower part, no? So we will just consider, let's say, this upper rectangle, no? Okay, so the eccentroidal moment of inertia of this is bh cubed over 12. So the base is 18 and the height is 2.25. Okay, and the centroid of this rectangle is here. No, so there is a distance between this point up to the reference axis. So there will be distance d. So the distance d will be half of 14.5, okay, plus half of the height of this rectangle, which is 2.25, right? So that distance, again, if we input in our calculator, half of 14.5, okay, half of 14.5 plus half of the height of the rectangle, which is 2.25, so 2.25 over 2. So the height will be, or the distance d, will be 8.375. No, so that will be the distance d here. Okay, so our area for that rectangle is 18 times 2.25. So we will just multiply it by 2. Okay, since we have two rectangles for this. No? So solving for Ix bar, so this will just be 7,681.99 inches to the fourth. So this will now be the answer for this. Now for Iy bar, okay, so which is the moment of inertia with respect to the y centroidal axis. So this is the y centroidal axis. Okay, so if you are going to solve for the centroidal moment of inertia of the first rectangle, no, so that is hb cubed over 12. So this will be hb cubed over 12. And then there will be no distance d, since the centroid of this rectangle is at the reference axis. No, so that will be 0. And then for the angle, okay, for the angle, let's just consider one angle here and then multiply it by 4. Okay, since we have 4 angles here. So for this angle, okay, so its y centroidal moment of inertia is 69.6. Okay, but the centroid of this is located here. So there will be distance d from the reference axis. So the distance d, to compute that, that will just be half of this, no, half of the thickness of this, which is 1, no, half of that is 0.5. So 0.5 plus this distance. So this distance is x bar from the table. So that will be 0.5 plus 3.05. So 3.05 plus 0.5, that is 3.55. So that is the distance d. Okay, so this will be that distance d. And our area is 11. Okay, so we will multiply it by 4 ha, since there are 4 angles. Now, for the rectangle, okay, so these two rectangles, they are identical, so we will just multiply it by 2. So the y centroidal moment of inertia of these rectangles are hb cubed over 12 also, wherein h is 2.25, our base is 18. Okay, so there will be also no distance d, since the centroid of these rectangles, okay, are located at the reference axis y. y centroidal axis. Okay, so that will just be 0, the distance d. So solving for this, we can solve for IY bar. So our IY bar is 3,021.08 inches to the fourth. So this will now be the answer. So that concludes our discussion for this lesson. I hope that you learn and I hope that you attain the learning outcomes and the concept. No, so this will be very important. So this will be our last discussion for this term. And I hope that you learn from the entire term. Okay, so I hope to see you soon, class. No, maybe sa next subject mo. No, and also, no, to just to conclude this, I'd like you to comment, no, everything that you learn, no, not just for this discussion, but for the entire term, no, for this course, no. Please comment down, no, in the comment section your thoughts about your learning, about your experience in this course. Okay, so thank you, class, and God bless, and see you soon, engineers. God bless. Bye bye.